Okay. Okay. So we are going to start today's lesson with a warm-up, a little problem exploration. So I want you to find the radius of a cone that has a volume of 11 cubic inches and a height equal to twice its radius. I want you to leave the answer in pie format and do not leave any radicals in the denominator. Okay, so this seems a little tough right now, especially because when you go to solve, you don't quite know how to get those radicals up out of the denominator. So that's going to be one of the primary focuses of our lesson today. So that's going to kind of tell you where we're going to end up being able to do this problem. We're going to be able to, by the end of this lesson, be able to tackle this problem. Okay, so this leads us to what we're talking about today. These are notes 5C2. They are over roots and radical expressions and multiplying and dividing radical expressions. Okay, so here's the real takeaway we need to have from this slide. You don't need to write it down, but just I need you to kind of just stop and think for a second. So if we have a to the nth equals b, then to solve that, we're going to take the nth root. Just like if it was a squared equals b, we'd take the square root of both sides. If it was a cubed equals b, we'd take the cube root, and so on. So that exponent on n becomes the index of the root when we go to solve. So if n is odd, like 3, 5, 7, so forth, if that index number is odd, then there is only going to be one real root of the nth root of b if n is odd. Because think about it. The cube root of -8 is -2, because -2 times -2 times -2 is -8. There's no other choice that it could be. There's no other solution that it could be. However, if n is even and b is positive, meaning that's a positive number underneath that radical, if n is even, there are two real roots. We have the positive root. You'll hear me call it the principal positive or the principal root. And its symbol is the nth root of b. The negative root is the negative root. So, you know, like when we're solving for x and it's like x squared equals 4 and we take the square root. If we take the square root, then we have to put the plus or minus. And this is why. Because like if we're solving for x and it's x squared equals 4, we take the square root, well, it could be +2 or it could be -2. Both of those solutions work. So you're going to have to be doing plus or minus if you actually put the root on and n is even. Okay, but if n is odd, it just is what it is. There's only one. But if n is even, then you've got to consider the positive and negative values. Okay? The other thing, always assume all variables are positive. So during this chapter, we want you to assume that all variables are positive. So finding all real roots. So we're actually finding the roots, okay? So for example, if I ask you, what is the real cube root of -1000? The real cube root. So I'm putting the cube root there, but it's odd. So it would just be -10 because -10 cubed is -1000, okay? But what if I asked you what is the fourth root of 16/81? Well, I'm putting the fourth root there. I'm putting the radical because I'm trying to solve for it. And since I'm putting the fourth root there and the fourth root is even, it has to be plus or minus 2/3 because I put the radical there and the index is even. So plus or minus 2/3 is your answer because 2/3 to the fourth is 16/81 and -2/3 to the fourth is +16/81 as well. Okay. And then here, what is the real fourth root of negative 0.0001? Now, and this is something kind of we didn't really touch on from the last slide, but if it's an even index, think about it. If I was taking the square root, can I take the square root of a negative number? No. So that applies to all even index roots. If you are taking an even index root, like square root, fourth root, sixth root, eighth root, if your index is even and the number underneath is negative, then that means you have no real fourth roots. No real fourth roots. So if your index is even and the number under the radical is negative, there are going to be no real roots. You'll have imaginary roots, but you won't have real roots. Okay? Okay, so the only thing you need to write really from this rule up here, we're now going to move on to multiplying radicals. Now, really what you need to write, this is the main rule, it's the part that comes after the then, is that if I have the nth root of A times the nth root of B, that becomes the nth root of AB. Now, here's the catch. Those n's have to be the same value. So you can't multiply a square root times a fourth root. Can't do it, okay? I know on day one, yes, you can change it to rational exponents and do it that way, but if you're leaving it in radical form and you're multiplying them, the index number has to be the same. Okay, so to multiply radicals, the index number has to be the same, and then you can multiply them. Let's look at example 1. Now, you're like, okay, the index numbers are the same. Here's the catch. It only has to be the index numbers. We don't care if the stuff underneath is the same. That does not have to be the same. But to multiply radicals, the index numbers have to be the same, which in this case, they're both 4, so we're good to go. So all we do, we don't mess with the index numbers, is we multiply the numbers underneath. So I get the fourth root of 16. Now I have to go, okay, is there a fourth root of 16? And the answer is yes, because 2 times 2 times 2 times 2 is 16. So the fourth root of 16 is 2. Pretty simple. Let's look at example 2. So I have the square root of 35 times the square root of 72. So they're both square roots, so I can multiply. And when I multiply them, I get 2,520. Now, before you start panicking, yes, we need to simplify it. We can't leave it like this. So I start out with 2. 2 times 1260. 1260 breaks down into 2 times 630. 630 breaks down into 2 times 315. But I can no longer divide by 315, so I have to start by 3's. And that gets 3 times 105. 105 breaks down into 3 times 35, and 35 breaks down into 5 times 7. Now, because this is a square root, I have to circle in groups of 2. So as long as I have 2 of the same number, I can circle them and they get to come out of the radical. So there's a 2, and then I have 2 3's. So the 2 and the 3 get to come outside of the radical because 2 times 2 is 4, square root of 4 is 2, 3 times 3 is 9, square root of 9 is 3. So 2 and 3 come outside. However, 2, 5, and 7, they didn't have a buddy to be circled with. So they stay back underneath the radical. So 2 times 3 is 6. And that gets 6 square roots of 70. Now you're probably wondering, why didn't we put the plus or minus? Here's why we didn't put the plus or minus. Because we did not put the radical there. We're not solving. We only put the plus or minus if we're solving and we put the radical there. But in this case, we didn't put the square root there. He was already there. So it's just the principal positive, 6 square roots of 70. Okay, let's look at example 3. Example 3 is 2 square roots of 12 times 3 square roots of 2. Now, the thing about multiplication is it's commutative, meaning it doesn't matter the order that you multiply them in. So when you're multiplying two radicals, first of all, the index numbers have to be the same, which they are. They're both square roots. To multiply, you can multiply the coefficients and then you can multiply the radicals. So if there is a coefficient outside of that guy, you multiply them and then you multiply what's underneath the radical. So in this case, 2 times 3 is 6 and 12 times 2 is 24. But we're not done, because you always want to look and go, well, can I simplify 24? Can I simplify the inside more? And the answer to that is, yeah. So 2 times 12, 12 is 2 times 6, 6 is 2 times 3. So it's the square root, so there has to be 2 of them. Okay, so that becomes 6 times, because the square root of 24 is 2 square roots of 2 times 3. Now, 2 times 3 is 6, and then 6 times 2 on the outside is 12. So I did 6 times 2 got 12, and then the 2 and the 3 got multiplied back underneath the radical to be 6. Now, let's look at example 4. Example 4 is 2 plus the square root of 12 quantity squared. So remember, anytime you see a parentheses squared, that means, hey dude, write me twice. And now I have to FOIL. Question, can you box? Absolutely. You do whichever method makes the most sense to you. Okay? You do whichever method makes the most sense to you. So I'm going to FOIL this, and this is what I get. I get 4 plus 2 square roots of 12 plus 2 square roots of 12. And then, of course, square root of 12, square root of 12 is square root of 144. Now, square root of 144 is 12. And then 4 plus 12 is 16. Now, you're probably wondering, oh my gosh, did I have to show that first step where it was 4 plus 2 square root of 12 plus 2 square root of 12 plus 144? Answer, no. If you can do that in your head, then you can skip down to the next step. That's fine. But again, I do want you showing some work, because don't try to, if this was any old other FOILing a binomial, it wouldn't be an issue. But because we've got radicals and signs, you're more likely to make a mistake if you don't show some work. So I'd rather you show too much work, or what you feel is too much work, and get the question right, than not show enough and you drop a sign or you mess up a radical or something like that. So always show your work. So I have here 16 plus 4 square roots of 12. Now again, you always want to look at your ending radical and go, can he be simplified more? And the answer to this case is yes, because it's the square root of 12. So 2 times 6, 2 times 3. The 2's get circled, so they get to come outside. And I get 16 plus 4. Now the square root of 12 has now become 2 square roots of 3. So I've got a 4 also, so I just have to multiply 4 times 2, and I get 8. And that is my final answer. Okay. Let's talk about dividing. Now, again, you don't have to write all that stuff before. The main thing you really need is the formula that comes after then, the word then. So what it says is, if I have the nth root of A divided by the nth root of B, I can combine that to be the nth root of A over B, as long as the index numbers are the same. This whole section, it's like the index numbers have to be the same. Okay, now this rule works forward and backwards just like the multiplication one does. So if you look at it backwards, you can take the nth root of a over b and break it back into the nth root of a over the nth root of b. We're going to be using this rule forward and backwards throughout this lesson. Okay, so just get comfortable with if the index is the same, you can combine it into one fraction and take the nth root of that fraction, or you can separate it from one big fraction. So we're going to talk about probably the best time to do that and the best time not to do that. We're going to talk about that throughout this lesson. But just know you can take two nth roots that are being divided as long as the indexes are the same and combine them into one fraction and vice versa. So let's look at example 5. The cube root of 54 over 2. Now, here's the rule for combining. Only combine if it's going to help you. If combining that's not going to help you in any way, shape, or form, then I wouldn't do it. But like this time, I'm like, well, if I combined it, I know 54, 2 goes into 54. So I'm going to combine that into the cube root of 54 over 2. Because I know that's going to help me because 54 over 2 is really 27. So I now have the cube root of 27. See how that made it a little bit easier for me? And I know that the cube root of 27 is actually 3. So it helped me in this case to combine them. Okay, let's look at example 6. So, well, 6 goes into 24, and I can probably clean up those x, y's, and z's. So let's combine that into the square root of 24 x to the 7th, y to the 5th, z cubed divided by 6xyz. Now, I know 6 goes into 24 4 times. That x on the bottom will subtract with that x on the, well, we'll divide, and then we subtract the exponents and make that x to the 6th. Same with the y becomes y to the 4th because y to the 5th over y is y to the 4th, and z cubed over z becomes z squared. So by combining this, we were able to simplify the inside and then also get rid of the denominator. So here's the deal. When we take the square root, so the square root of a number is pretty straightforward, okay? But when you take the square root of variables with exponents, you basically take that index number and you divide the exponent by that index number, okay? So square root of 4 is 2. What times itself would give me x to the 6th? X to the 3rd, right? Because 6 divided by 2 is 3. Same with y and same with z. So square root of 4 was 2. Square root of x to the 6th was x cubed, x cubed, x cubed. Square root of y to the 4th was y squared because y squared times y squared. And square root of z squared is z. And again, I'm going to show you, again, we're going to get more into that little trick of the dividing. So basically the trick is you take the index and you divide the exponent by the index. And you're like, well, that's all fine and dandy if it goes in even. What if it doesn't? We're going to show you what happens. So let's look at our next slide, example 7. So, example 7, simplifying radicals. Now you're like, well, I know how to do it if it's a number. Awesome. What if it's a variable with an exponent? How do we handle that? So, let's look at this problem. The cube root of 32 m cubed p 6th q to the 5th r to the 7th. Now, for the number, it's pretty straightforward. That has not changed. 2 times 16, 2 times 8, 2 times 4, and 2 times 2. However, this is not a square root. This is a cube root. So remember what we talked about on day 1. That index number tells me how many have to be in my circle. So this 3 tells you how many you need in each group. So I've got a 3, so there's got to be 3 of the same number in my group. So right away I see that. And then I notice I was like, well, I've got 2 left over, but there's not 3, so they have to stay in the radical. So, and then bear with me. If you don't want to write this part out, you don't have to because I'm about to show you the shortcut. But check it out. So that gets me the 2 outside on the cube root. I have the 2's left over on the inside. M to the third is really m times m times m. P to the sixth is p times p times p times p times p times p. Q to the fifth, you get the idea. I just wrote this out, expanding it. Now, going off the idea that I can circle in 3's. If I have 3 of one variable, I'm going to circle it. Now, so you see that I had 1 group of m's, 2 groups of p, 1 group of 2, but I had 2 q's left over, so they got to stay underneath the radical. 2 groups of r, and then 1 left over, so he's got to stay as well. So I pull that m out. I pull the 2 p's out, so p times p becomes p squared. I pull out the q, and then I pull out the 2 r's to become r squared. And so you get 2m p squared, because 2 sets of p's came out, 1 set of q's, 2 sets of r's, and then if you look at what I had left over, I had 2 times 2, which is 2, q times q, q squared, and r. Now that's a lot of work. I'm not going to lie. I wouldn't do that. That's a lot of work for one problem. So what we're going to do is I'm going to show you a shortcut. I think you're going to like this method a little bit better because it's shorter and it's easier. So we're going to go back to the same problem we were just doing. And the factor tree for the coefficient, that doesn't change. So I'm going to pop these rules up, and then, but before I actually get into the variables, I'm going to write down the number. So I had a set of 3 2's that came out as 2. I had 2 left over, so that becomes 2 cube roots of 4. Now, the rule is you take the exponent on the variable and you divide it by the index. How many times it goes in evenly goes on the variable outside. If there's any remainder, that variable also goes back inside, and the remainder becomes the new exponent inside. So let's look at m to the third. How many times does 3 go into 3? 1 time. So the m comes outside. There's no remainder, so I don't put a remainder out. Okay, let's look at p to the 6th. 3 goes into 6 2 times evenly, so that becomes p squared on the outside. There's no remainder, so there's no p left on the inside. Let's look at q to the 5th. 3 goes into 5 1 time, 2 remainder though. So q to the first comes outside, but because I have a remainder of 2, that 2 becomes the exponent on the inside. And lastly, 3 goes into 7 2 times, so r squared on the outside, remainder of 1, r to the first on the inside. So 3 goes into 3 1 time, no remainder. 3 goes into 6 2 times, no remainder, so p squared on the outside, no p on the inside. 3 goes into 5 1 time with a remainder of 2. So q to the first on the outside, q squared on the inside. 3 goes into 7 2 times with a remainder of 1. So r squared 2 times, r squared on the outside, r to the first on the inside. And that's a little bit easier. The more you do it, the more you get comfortable with that, it's going to be easier. Now, common question. What if I had something like x squared inside? Well, 3 doesn't go into 2 at all. So you would leave that on the inside. So if you have some number that the root doesn't even go into it, like 3 doesn't go into 2, then you just leave it alone and nothing gets to come outside there. Okay. talk about simplifying the square root of x squared plus 10x plus 25. Now, you're going to want to pay attention to this. I'm not saying where. I'm not saying when. I'm just saying you might see this again in your very near future. I'm just saying. So you might want to make sure you know how to do this. Now, you cannot take the square root of the individual terms. It doesn't work that way. What you have to do on the inside, whenever you have a trinomial on the inside, is more often than not, if you're taking the square root of a trinomial, more often than not, it's going to be a perfect square trinomial, meaning it is a binomial times itself. Okay, so what you have to do here is you need to factor that trinomial. So what two numbers multiply to make 25 that add to make 10? 5 and 5. So that's going to be the square root of square root of x plus 5 times x plus 5. Now you're like, well, how does that help me? Remember, oh my gosh, remember when we kind of did something like this without the square root? To complete the square, we wrote it like this, and then we combined it into one parenthesis squared. Something times itself is that parenthesis squared. So now that we're taking the square root of it, the square root of the parentheses squared is just the parentheses, x plus 5, and you're done. So if you're asked to simplify this, first thing is you want to factor it out. If they're identical, bring them in to be that parentheses squared, and then when you take the square root of the square, it's just x, in this case, x plus 5. So let's get into rationalizing the denominator, okay? So we know, and you know this from your geometry class, like when you were doing 30, 60, 90s and 45, 45, 90s, we know that we cannot have a radical in the denominator. Can't do it. We have to rationalize the denominator. So that's what these next few slides or next couple of slides, we'll go next three slides. That's what they're about, rationalizing the denominator. So this fella, let's look at this guy. Him being combined is not helping me. I can't simplify 16 over 5. It just doesn't work, okay? And no, please don't write it as 5 1/3. So 16 over 5, can't do it. So I'm going to use that division rule, and I'm going to break him apart into two separate square roots. So I get the square root of 16 and the square root of 5. Well, yay! I so know that the square root of 16 is 4. And again, we're not putting plus or minuses here because we didn't put the roots. The radical was already there. Okay? So that becomes 4 over the square root of 5. Now we know that is so not legal in mathematics. Can't leave it like that. It doesn't work. So we're going to have to do, which is what this guy says, we are going to have to rationalize the denominator. We're going to have to rationalize the denominator. Now, square roots, that'll look familiar, but then we're going to get into what if it's a cube root? What if it's a fourth root? So we're going to talk about that. But here's the deal. When rationalizing the denominator, you're going to multiply the denominator by the number of radicals that you need to form a perfect square, a perfect cube, etc. So, before I read on, I want to point out, when counting, you have to count the one you already have. He's already there. He counts. He counts as 1. So, if you have a square root, then you need one more additional root, because two square roots being multiplied together, if they're the same, make a perfect square. If it's a cube root, then you need 2 additional roots, okay, because you've already got the one that's there, and then you need 2 more to have 3 on the bottom. Okay, if it's a fourth root, you need 3 because you've already got 1, and then you put 3 more. Now you've got 4. Okay, so really there's not really a formula, but if you think about a formula, to tell you how many additional roots you need, it's just basically the index number minus 1, n minus 1. Okay, so if your index is 2, then 2 minus 1 is 1. You only need 1 more. If it's a cube root, 3 minus 1 is 2, so you need 2 more. if it's a fourth root, 4 minus 1 is 3, so you've got to put 3 more on. Now, here's the other thing you want to make sure of. If you multiply the denominator by a square root, you also have to multiply the numerator by that exact same square root. Because if you don't, it's no longer the same fraction. Okay? So whatever you do to the bottom, you got to do to the top, because that's really just a special form of 1. So again, doing a little plastic surgery on it, not changing its value, not changing who it is, just changing what it looks like. So in this case, I have one radical and it's a square root, so I only need one more. So I'm going to multiply the bottom by the square root of 5. But again, if I multiply the bottom, I have to multiply the top. So up top, that gives me 4 square roots of 5. On the bottom, that gets me the square root of 25. But wait, what's the square root of 25? 5. So your final answer is 4 square roots of 5 over 5. And you're done. So square roots, not that bad. But what if it is a cube root? Now the first thing, okay, be it a square root, a cube root, fourth root, whatever the situation is, the first thing is if you've got like variables and maybe some like, well, in this case, the coefficients don't really have anything in common, but if you've got like variables underneath that radical, under both of them, let's combine them. Always combine into one and see if you can simplify underneath first. So, because I've got x's in both, I've got y's in both. So combine it into one, even if it's just temporary, combine it into one, and let's see if we can simplify. Now, like I said, 3 over 5, that doesn't reduce. We can't do anything with it. Yeah. But look at, we have x to the 7th over x cubed. So if we subtract those, that becomes x to the 4th on the top. With the y, it's y to the 5th over y squared. So that's going to be 5 minus 2 is 3. That's going to be y cubed on top. So when we simplify the fraction, I get 3x to the 4th y cubed over 5. Now, I've done all I can do with that. I can't simplify it anymore, so now I'm going to break it back up. So you combine it and simplify it, and then break it back up. So, let's see here. Can I simplify the radical on top? Well, there's no cube root of 3, but 3 goes into 4 one time with one remainder, and 3 goes into 3, right? So I left the 3, but 3 goes into 4 one time with a remainder of 1, so x to the 1st on the outside, x to the 1st on the inside, and 3 goes into y, or into 3, one time for that y with no remainders. So I've simplified the top. We already know the bottom simplified, but you might always check. In this case, we can't simplify 5. So now, we've combined it, simplified inside, split them up again, and then we saw if we could simplify anymore. Now everything's simplified as much as it can be. Now let's get on to rationalizing that denominator. So it's a cube root of 5. So I already have 1. So to get 3 across the bottom, that means I just need 2 more, because 3 minus 1 is 2. But remember, if you multiply the bottom by the cube root of 5, you got to multiply the top. So I'm going to rationalize that denominator. There's 1. There's 2. So across the top, I get xy, and then 3x times 5 is 15x, times another 5 is 45x. Across the bottom, I have the cube root of 125. Now, I'm going to check, because I know I can't do anything with that x. He's done about as much as he can do. But I'm going to see, can I simplify 75? No, because there's not 3 of anything. I have 1 3 and 2 5, so that's not going to work. But I do know the cube root of 125 is 5. And that's as far as I can go. That is as far as I can go. It's all about simplifying as you go. Okay, taking it one step at a time. Don't try to do more than one step. You've just got to work it out step by step by step. Let's look at example 11, another one. So this guy, what I'm going to do is, I see I've got some couple of y's there that might work out. So I'm going to combine that into one fraction. Combine that into one radical with one fraction. X cubed won't simplify, but I'm like, y squared and y will. So the y on the bottom cancels out, leaving me with y to the first on top. And unfortunately, that's all we can simplify. There's nothing else. So we're going to break it apart. Break it back up apart. Now, this way, now I could have, if I'd wanted to, pull that x outside, but probably wouldn't have done me much good. It's not going to hurt if you go ahead and simplify it this step. But I think instead, I think I'm just going to go ahead and jump in and rationalize that denominator. Now, again, if you'd rather pull that x out first and just have the cube root of y, that's perfectly fine. No harm, no foul. I'm just going to leave it in for right now because, one term. So I'm going to rationalize. Now, this is a cube root of 2z squared. So I have 1 cube root. I need 2 more of them to have 3 cube roots on the bottom. So if I multiply the bottom by 2 cube roots, I've got to multiply the top by those 2 cube roots. There it is. Okay, so, and it's always the denominator over the denominator, because again, that's 1. So I rationalize with 2z squared over the cube root of 2z squared times the cube root of 2z squared over the cube root of 2z squared. So now they're all cube roots, so I can multiply them. So that becomes 4x cubed y z to the 4th all over 8z to the 6th. So let's see. I know 4 won't simplify, but 3 goes into 3 evenly. 3 doesn't go into y, so into the y to the first, so we leave him. But 3 goes into 4 one time with a remainder of 1. So it looks like that. So you can see 3 went into x one time, no remainder, so nothing inside. 3 didn't go into y to the first, so we left it. 3 goes into 4 one time with 1 remainder. And we already said there is no fourth root of, there is no cube root of 4. So we left the 4 inside. And then, of course, cube root of 8 is 2. 3 goes into 6 2 times. So that's where we're at. And you're probably thinking by now, oh my gosh, I am so done. No, you're not. Because check it out. I can still simplify the outside now. You can't touch the radical. He's as far as he can go. But if you notice, I have an xz over 2z squared. So that z in the top will cancel out with one of those z's in the bottom. And you're left with x cube roots of 4yz over 2z. And now you're done. Okay, so this problem looks familiar, and it should because it's the warm-up problem. Okay, so now we're going to get to work it. I told you by the end of the lesson, we're going to get to work this. So we want to find the radius of a cone that has a volume of 11 cubic inches and a height equal to twice its radius. Leave it in pi format, no radicals in the denominator. So we gave you this formula. Now, right away, I see that I have a volume of 11, so 11 will go in for the volume, 11 cubic inches. Now, this is the other key part. The height is equal to twice the radius. So I'm not going to leave the h in there. I'm going to change the h to 2r because the height is equal to twice the radius. So I'm going to sub in those two values 11 for volume, 2r for height. Okay, so when I combine these, you're probably thinking, well, should I multiply 1/3 times 2? You could, but why? So we'll just leave them separate for now. So I can combine r squared and r to get r cubed. So first thing I want to do is I want to get rid of that 1/3. So I'm going to multiply by 3. Cancels that out. But on the left, I end up with 33. And on the right, I'm left with 2 pi r cubed. So to solve for r, I need to isolate r cubed. So I have to divide by 2 pi. So that gets me 33 over 2 pi, because the 2 pi's on the right cancel. And that equals r cubed. Well, I want r by itself. So to undo cubing something, just like if I undo the square, I square root it. So to undo the cube, I'm going to cube root it. So I get the cube root of 33 over the cube root of 2 pi. Now, can't leave that radical on the bottom. So it's a cube root. There's 1, so I need 2 more. But if I multiply the bottom by the cube root of 2 pi twice, I have to do that to the top as well. So cube root of 2 pi over cube root of 2 pi times cube root of 2 pi over cube root of 2 pi. Now you'll notice I now have 3 cube roots identical on the bottom. So up top, I end up with, let's see, 33 times 2 is 66. 66 times 2 is 132 pi squared over 8 pi cubed. But on the bottom, that becomes 2 pi. Now, I can't simplify 132 over pi squared because that's 3 times 11 times 2 times 2. There's not 3 of anything. And, of course, 3 doesn't go into 2. So we just have to leave that exactly as it is. It is simplified. It's done. Okay? So that's as far as you can go. And that's what your radius is in terms of pi with no radicals in the denominator. Okay, so now I want to see, do you really get it? Do you understand it? So let's look at these 5 problems. I want you to pause the video right now, and I want you to try these 5 on your own. Okay? Then I'll reveal the answers. And of course, on the last 2 slides, I have all the work. But I want you to try them first on your own. You're never going to know if you don't get it or if you get it until you do it on your own. So pause the video and then hit play again when you're ready to see the answers. Okay, so let's look at the answers. This is what I got. Now, the one I really want to call your attention to is that last slide, or excuse me, that's that last slide, that last simplify. 3 over 2 square roots of 6. Now, I know some of you might have been tempted to do 2 square roots of 6 over 2 square roots of 6. And you could. That's perfectly fine. But that 2, he's perfectly legal in the denominator. The only thing you cannot have in the denominator is that radical. The 2, he's fine. But the square root of 6, he's not fine. So I did it by square root of 6 over square root of 6. But again, if you did 2 square roots of 6 over 2 square roots of 6, that's fine. You're just going to have a little bit more simplifying in your future. So here's the answers. Now let's flip over and let's look at the work. So here's the first one. I showed you how I broke down 24. And that's how I came up with the answer. 3 went into 3 once, no remainder. 3 doesn't go into 2, so we left y squared. 3 goes into 4 one time with 1 remainder. On the second one, I simplified underneath that radical first. 3 goes into 24 8 times. The x's cancel, and the y's left in the denominator. Okay, so again, 24 over 3 was 8. X is canceled. Y is in the denominator. Now, I've gone as far as I can in terms of simplification, so I'm going to break them back apart. And that gets me the cube root of 8 over the cube root of y. I rationalize my denominator. And that gave me the cube root of 8y squared over the cube root of y cubed. Now, you're probably wondering, up on that kind of middle step, could I have just taken the cube root of 8 and said 2? And the answer is, So, again, different steps. If you'd rather take and make that 2, and then you just have the cube root of y squared, that's perfectly fine too. Matter of personal choice and how you chose to solve it at that time. So when you clean it up, back to the way I did, I of course took the cube root of 8. 3 didn't go into 2, so we left y squared underneath, and then the cube root of y cubed is y. This third one on the top left, that was just one of those perfect square trinomials. And then the fourth one, you just had to FOIL. And you'll notice that I didn't multiply 27 times 27. No way, I'm not taking time to do that, because the square root of 27 times the square root of 27 is square root of 27 squared, which is just 27. So I saved myself some work. And then on the bottom, it's the square root of 6. So we rationalize square root of 6 over square root of 6. And I get 3 square roots of 6 over 2 times the square root of 36, which is 2 times 6. Which is 12, and 3 goes into 12 4 times. So, again, you could have on this one done 2 square roots of 6 over 2 square roots of 6. It's just going to involve a little bit more work when you reduce, but, you know, it's not terrible. Okay, so this is where we come to the end of the video. We're done. Okay, and your homework is 5C.2. All right, have a good one.